All right, howdy. So I'd like to look at resistor networks. We're going to put lots of resistors together and see what we can do about solving some problems. This will culminate in the last example, which is probably the hardest example that I'm going to give for the entire semester. I'm not completely sure. There might be a harder one later on, but I rather doubt it. It took me a lot more work than most of the other ones. So that one's going to be the longest example, probably in the course. A resistor network is something where you have lots of resistors in sort of a random order, or at least as far as you're concerned, a random order. So something like this. Probably should have used little boxes instead. Sometimes you do. So we have all these resistors doing all these sorts of things, and you might have different voltages, V0, V1, and 0, or something like that. And then you're supposed to figure out, what is going on over each one of these resistors. So that's what the resistor network is. I wonder what that was. We're not going to start with something that complicated. We'll start with something fairly simple. It's actually something we may have talked about. I don't remember at this point. And if we didn't talk about it yet, then it's implied by something we've already talked about. It's definitely implied by something we've talked about. And that is, if you have two resistors in series, like this, 1 and 2, so this is resistor 1 and this is resistor 2, and then you connect them to a battery here, right, with the rating of V0, and we can go ahead and give this a ground there. Then the voltage drop from here to here, or from here to here, is proportional to the percentage of the resistance for each one of those things. So that means that this is R1 plus R2 times V0. This one's R2 times that same V0 over that same sum, the sum of the resistances. Okay? And this is just like when we talked about the wire, and we said, if I have, say, 1/3 of the wire here, then the voltage drop here is completely linear. So this is going to be 2/3 of V0. And this will have a voltage drop of 1/3 of V0. It's pretty much the same thing. You can take each one of these resistors, if you would like, and pretend like it's a long piece of wire at this point, right? Probably for this entire class. We're not going to do anything where we have to worry about the configuration of the resistors. So, or how the resistor is actually built, how the resistors interact with each other. Things will get a little more complicated if you take those kinds of engineering courses. So these two guys here add up to 1 V0. So if this is connected to this battery here for V0, the longer part, that's 2/3 as long as the latter part, which is shorter part, which is 1/3 of the length, has the greater voltage drop. The same thing would happen here. This is all this is saying. So 2/3 plus 1/3 is 1, right? So that's 1, and this is 2/3, so that's 2/3. 2/3 over 1 is 2/3, so it's 2/3 V0. So just like in the wire, you can figure out what's going on with the potential drop. For the same reasons, you can find the potential drop in each one of these, just by pretending that the resistors are, just by pretending that the resistors are long wires, all right, long pipes, whatever you want to think about. So that is number 1. The voltage drop over a resistor in series is proportional to its share of the total resistance. Okay, that seems reasonable to me. And that just means that your delta V for resistor I is equal to the resistance of I over the sum of all of the possibilities. That shouldn't be an I, and it should probably be a J. So over all of the resistors times the actual potential over the potential drop over the two terminals between the start of the first resistor and the end of the last one. Okay, so it's pretty simple. Start that one off a little bit easy. I'll do an example of that with just something very much like that. Find a resistance from knowing some other stuff about the circuit. Okay, so that's how we'll start. Then next time I'll talk a little bit about one of Kirchhoff's laws, the junction law, which will say that all the current coming in is equal to all the current coming out of a junction. Charge does not accumulate when you put two wires together in a circuit. Charge won't accumulate there, it'll keep flowing. And the last one will be the voltage rule, or the loop rule. The loop rule says basically that every point in the circuit has a unique voltage, right? So it's going to be sort of like a height, right? And that is going to say that whenever we trace something around, we can add and subtract voltages to get a relationship between them. So the next two things will be algebraic laws, that will sort of tell you how to analyze circuits. Right? And that's one of the things we do in this class. It's not really hard, but basically what they do is they give you the formulas that you can use out in algebra. They give you the formulas you can use with algebra to determine things about the circuit. Usually currents going through this part or that part of the circuit. All right? Bye now.